All right, welcome to this explainer. Taking dense, highly technical engineering standards and transforming them into something actually practical and actionable, that's what we're doing today. We are decoding ISO 3183, specifically the 2019 4th edition. Now, if you're a pipeline engineer, a procurement specialist, or a pipe manufacturer, keeping up with international specs can honestly feel like learning a completely new language, but it really doesn't have to be that way. We're going to break down exactly what you need to know to make sure your steel pipes are perfectly compliant for petroleum and natural gas systems. Let's get into it. But before we map out the details, I want you to ask yourself a critical question about international compliance. API Spec 5L sets a phenomenal global standard, right? No doubt about it. But what happens when your pipeline is routed through Europe and requires an extra layer of regulatory rigor? Well, the answer lies in the highly specific, localized requirements embedded deep within the ISO documentation, which we are going to uncover today. So, here is our roadmap for today. Number 1, the ISO and API connection. Number 2, ordering and marking pipes. 3, European pipeline standards. 4, manufacturing rules. And finally, number 5, the testing gauntlet. Okay, section 1, the ISO and API connection. Here it is, the standard itself, ISO 3183, the 4th edition from 2019. This is the international benchmark for seamless and welded steel pipe in the petroleum and natural gas industries. Sure, it looks a bit intimidating at first glance, but its actual purpose is just to create a unified, incredibly safe global infrastructure. Now, historically, API Spec 5L and ISO 3183 were identical documents. But when API updated to its 46th edition back in 2018, things shifted. ISO 3183 adapted to act as a vital supplement. Think of it like taking the API 5L baseline playbook and layering on crucial updates, specific normative references, and most importantly, it introduces Annex A for European onshore natural gas pipelines. So if you're following ISO 3183, you're fundamentally working from API 5L, but with some very critical exceptions. Moving on to Section 2, ordering and marking pipes. When you're buying pipe on this level, you can't exactly just ask for some steel tubes, right? You have to be incredibly precise. The standard dictates that alongside your usual API requirements like grade and dimensions, you have to explicitly tell the manufacturer if Annex A, that European standard we just mentioned, applies to your order. You also have to dictate exactly how the pipes should be marked to prove their compliance. You can go with a strict ISO 3183 marking or opt for an API 5L marking with a monogram plus an additional ISO stamp. And let me tell you, a correctly marked pipe literally tells the whole story of its creation. Take a look at this sequence. X is the manufacturer's name. Then you have the standard, ISO 3183. Next up are the dimensions, 508 millimeters in outside diameter with a 12.7 millimeter wall thickness. L360M gives you the specific steel grade. PSL2 means it's a higher product specification level. SOL tells us it's a submerged arc-welded longitudinal pipe. And finally, Y and Z are the purchaser's inspection mark and the unique ID number that ties the pipe right back to its inspection document. Every single character matters here. Next up, Section 3, European Pipeline Standards. If you're building in Europe, Annex A requires some seriously strict chemical control for onshore natural gas pipelines. Notice that special E suffix in the steel grade names, like L245NE or L360NE. That E is a massive signal. It flags that the chemical composition of the steel might actually fall outside the standard API Spec 5L limits. By putting strict caps on elements like carbon, manganese, and vanadium, the standard ensures the steel maintains the specific weldability and toughness needed for European environments. If you see that E, it strictly conforms to Annex A. All right, Section 4, Manufacturing Rules. Once you're actually at this steel mill, this standard leaves absolutely zero room for error or corner cutting. Annex A explicitly mandates a clean steel practice. Manufacturers have to use basic oxygen or electric arc furnace processes. The steel must be what's called fully killed, which just means it's completely deoxidized to prevent gas porosity while it solidifies. And it has to use a fine grain practice for superior toughness. Oh, and for high-frequency welded pipes, the edges of the steel coil can't just be rough cut. They must be cleanly sheared, milled, or machined so they are impeccable before welding even starts. And all of these mandates translate directly into the physical dimensions of the finished product. There are extremely strict mathematical tolerances for the diameter and out-of-roundness of the pipe body. As you can see, as the pipe's outside diameter gets bigger, the acceptable margin of error shifts from a simple static millimeter measurement to tight percentages of the diameter itself. Manufacturers have to respect these precise boundaries because when these massive pipes arrive out in the field, they have to line up and weld together perfectly.
And finally, Section 5, the testing gauntlet. 0 degrees Celsius, literally freezing. This is the required baseline temperature for the Sharpie V-notch impact test for pipes following Annex A. They don't test these pipes at a comfortable room temperature. They chill them down to freezing to mimic harsh operating environments. At that temperature, a heavy pendulum strikes the pipe weld and the heat-affected zone. To pass, the steel has to absorb an average of at least 40 joules of energy without shattering. It's a brutal, brutal test of the material's toughness.
If that wasn't enough, next up is the flattening test, which is exactly as intense as it sounds. It's a 3-step mechanical squeeze to prove the pipe won't crack under immense pressure. First, the pipe gets crushed down to 2/3 of its original diameter, and absolutely no weld opening is allowed. Then it gets crushed further to 1/3 of its diameter, no cracks or breaks permitted. Finally, it's flattened completely until the opposite inside walls touch. Throughout this whole physical destruction, it can't reveal any hidden laminar imperfections or burnt metal.
Now, for the pipes that aren't physically destroyed as samples, they get to go through a rapid-fire sequence of high-tech verification. This is the non-destructive testing, or NDT protocol. Let's start with ultrasonic testing. Think of this like a high-powered sonar for solid steel. It pings high-frequency sound waves through the metal to make sure no hidden layers, separations, or laminar flaws exist inside the steel itself. It scans the main pipe body, the edges of the original coil, and those all-important pipe ends. If ultrasonic checks the body, then radiographic inspection is essentially a doctor's X-ray for the joints. Using traditional film or digital radiography that meets a very strict image quality Class B standard, this test looks right into the weld seam. It's hunting for microscopic cracks, lack of fusion between the metals, or trapped gas and slag. It is the ultimate proof of structural integrity for the weld. Rounding out the NDT gauntlet is flux leakage testing. By magnetizing the pipe, inspectors can literally see where the magnetic flux leaks out of the steel. This perfectly flags longitudinal imperfections, especially in seamless and high-frequency welded pipes that the other tests might have missed. So, what happens if the sonar, the X-ray, or the magnetic field finds something? Well, the ISO standard is totally uncompromising. If any pipe triggers an alarm during these tests, it is immediately deemed suspect. A suspect pipe cannot just be passed along and hope for the best. It has to be completely verified, properly repaired and retested, or just outright rejected. There are 0 free passes when you're dealing with volatile natural gas transportation. We've really journeyed from the bureaucratic paperwork of API and ISO all the way to freezing impact tests and magnetic inspections on the factory floor. So, as you look toward designing or sourcing your next petroleum or natural gas system, remember the gauntlet it has to survive. With standards this incredibly rigorous, ask yourself, is your procurement and inspection process truly ready to meet ISO 3183? Thank you so much for joining me on this explainer, and keep building to the absolute highest standard.